Okay, this is Mr. Peterson, and we're doing the final page 4 of the notes for Section 8.1 in Algebra 2. This first problem talks about a time in the 90s, the late 90s, when cell phone usage just skyrocketed, and it increased at a whopping 26% per year. So what we have here is 133 million to start with, so that's going to be your A value. We got to find this base, and then we got to decide when does what would it be in 2099 or 1999. So here we go. Here's the base calculations. It's 100%. There was an increase each year of an additional 26%, so that's going to be 126%. And you move your decimal to the left when you convert to decimal. So your decimal's here, and you convert by lose the percent sign, you move it to the left. Here's the base you're going to use. So we have y equals the initial amount, A, and that's 33 million people in 1995, times the base to the x power. X represents the number of years after 1995. Not sure which year I said. So what would the model predict for 1999? That's 4 years later. We're going to go like this. This is the first answer here. For part B, we're just going to use that. We're going to say y equals 33 times 1.26. And if you take this year, subtract the 1995, you get 4. And let's find out how much this is. So on my home screen here, I'm going to type 33. That stands for millions. And I'll raise that to the 4th power, and you get 83.18. 83.18 million users, cell phone users. Okay, there's a part C. It says, how does this compare with the actual figure of 86 million? So the model's prediction is slightly low, or slightly lower than the 86 actual. So 83 compared with 86. Okay, so the next one talks about the intensity of light as you go deeper in the ocean. The deeper you go, the less light makes it there, so that eventually you're in darkness as you go down into the ocean. And this equation here with a base of 0.975 models the intensity of light from 20 feet down to 600 feet down. The value of y is the percent of light from the surface that makes it down to that depth in feet. So if you get a 7 here, it means that only 7% of the light gets down that far. Okay, so what percent of light reaches a depth of 30 feet? So part A, you're going to go y equals 20 times 0.975, and the x is 30 feet. So we'll type this in and see what it gives us. 20 times 0.975 raised to the 30th power. And that is 9.4% of the light. And this is automatically in percent. You don't have to change anything. So only about a tenth of the light, 10% would be a tenth, makes it down to 30 feet down. So it gets pretty dim even at a depth of 30 feet. So how about 100 feet? And this is going to be a really small number here. I'm going to change the exponent to 100. And it's 1.6%. That's all that makes it down that far. 1.6%. And I went diving when I was in college to about 90 feet down. I didn't quite go this steep. And it was pretty dark down there. You had to have a flashlight to see things. Okay, a computer's initial value is $2,500. So they're telling us the value of A is $2,500. And it depreciates, means it goes down at a rate of 15% per year. So let's find the base. 100%, we lose 15% each year. So that's going to be 85%. So slide your decimal when you lose the percent sign to the left. This will be your base. So here's the equation. And according to the model, how much would the computer be worth after 5 years? So we're just going to put a 5 in for X. Little scrunchy there. That's still 2,500 there. Okay, let's find out the value of this computer after 5 years of using it. It shouldn't be worth that much. Certainly not worth the initial amount. And you lose 15% of the value each year, so that takes you down to about $1,100 and 26 cents, if you believe that you can be that accurate with estimating the cost of a computer. Okay, the city of São Paulo, Brazil is growing at a rate of 9.94%, less than 1% each year, and its population in the beginning year of 2000 was this amount. So that's your A value, the initial value. And let's find the base. The base is 100% of their population with an additional 0.94% added on each year. So it's 100.94%. And you slide your decimal back when you lose the percent sign. There's your base. So we're going to write the equation here, 17.8, those would be millions. And we want to find out the population in 2015, and that's 15 years later, so we're going to put a 15 right there. And let's see what this gives us. 17.8, 1.0094 raised to the 15th power. 20.48 million. 20.48 million. And it's the question down here is, would Sao Paulo be more populous than Tokyo? Tokyo has 26.4 million, so no. Sao Paulo's would not be as populous as Tokyo. They only have 20.5 million in Sao Paulo, whereas Tokyo is holding steady at 26 million. Boy, that's a lot of people. New York, by the way, only has 7 million people. So these places are huge. All right, so that does it for the notes for section 8.1.